All right, so last time we showed how we can derive the four kinematic equations shown right here using only algebra. Today we're going to be getting the same exact results. We're going to derive the four kinematic equations, but this time instead of just algebra, we're going to be using calculus to do it. So again, these equations only apply if A is a constant or delta A equals 0. Uniform acceleration. So again, we're going to start with the definition of some physical quantities. So x denotes a position in space. Delta x is a displacement, so the difference between two positions. And if we divide that by some amount of time, so if we start off at one location in space at one time, it takes us a certain amount of time to get to the other location. This is the average velocity. But since we're using calculus, we can shrink the delta, the window, the difference between the two positions in space and time to a differential. So we have dx over dt, and instead of the average velocity, this is equal to the instantaneous velocity. So dx dt is the instantaneous velocity. Now we can take a second time derivative of the position. So dx squared dt squared, d squared x dt squared, which is equal to dv dt, gives us the acceleration. So the time derivative of the velocity is equal to the acceleration. We know all this. This is just the definition of what acceleration is. We can take this, so a equals dv dt, and this is a fraction. We can rearrange it. Let's multiply both sides by dt. A dt is equal to dv. This is a very simple differential equation. All we need to do is integrate both sides. The integral of a dt is equal to the integral of dv. Bounds on the integrals. This is an integral over time. It's going to start from t equals 0 to some t equals t later. The velocity integral is going to go from the velocity at t equals 0, which is the initial velocity vi, to the velocity at some later time t, which let's call vf. And this is, remember, a is constant, can come out of the integral, does not depend on time. A, the integral of from 0 to t of dt is equal to vi to vf of dv. This is a times delta t evaluated from 0 to t is equal to delta v evaluated from vi to vf. A times t minus 0 is equal to vf minus vi. Let's add vi to both sides, and we arrive at vf is equal to vi plus a t, and that is our first kinematic equation. The final velocity is equal to the initial velocity plus the acceleration times the time it takes to get to accelerate from the initial velocity to the final velocity. Okay. I'll put that box back up in this corner and I'll label, so VF equals VI plus AT, and this is equation number 1. And there will be 4. The second equation, let's start with the first. So VF equals VI plus AT. This need not be the final velocity. It can be the velocity at any point in time. So we can treat it as a function of time. V of t is equal to VI plus AT. Maybe you want to know what the velocity is halfway between these two quantities. So then you would need the time halfway between them. If you plug that in, then you get the velocity halfway along the journey of whatever's moving. And V of t, V is nothing more than dx dt. It's just the definition. So let us substitute that for V of t. So dx dt is equal to VI plus AT. And then how about we multiply both sides by dt? Get rid of the fraction. We're going to have dx is equal to VI dt plus AT dt. This is a differential equation. It's also very simple. There's just another term that we need to integrate. So let's go ahead and do that. The integral of dx from some initial position xi to the final x position xf is equal to the initial the integral of the initial velocity dt from t equals 0 to some later time equals t, plus another term at dt. Again, same bounds, it's a time integral, t equals 0 to t equals t. This is the left hand side becomes delta x, which is xf minus xi. Delta x evaluated from xf to xf to xi is equal to, vi is a constant, it's just a parameter of the problem, or a given value in the problem. It's a constant, it comes out of the integral, it doesn't depend on time. And then this will become dt, so vi delta t from 0 to t, plus another term. Acceleration is constant, it comes out of the integral. The integral of t dt, this will be t squared over 2, evaluated from t equals 0 to t equals t. A t squared over 2 from 0 to t. Okay, let's plug everything in. Xf minus xi is equal to vi times t plus 1/2 a t squared. And then let's add xi to both sides. So the final position is equal to the initial position plus the initial velocity times time plus half the acceleration times time squared. And this is our second kinematic equation. Our second derived kinematic equation, I'll place it in the box. Number 2. Okay, the third one is going to come from an interesting place. So the definition of acceleration is dv dt, and the definition of velocity is dx dt. How about we solve for dt in both of these and then set them equal to each other? So dt is clearly dv over a. dv over a equals dt, and dt is also equal to dx over v. dx over v. Let's get all the v things on one side. v dv is equal to a dx, clearly. And then this is just a simple differential equation for us to solve. Integrate both sides. The integral of v dv from some initial velocity to some final velocity is equal to the integral of a dx from some initial position to some final position. The integral of v dv is nothing more than v squared over 2, evaluated from initial velocity to final velocity, and this is equal to a is a constant that comes out of the integral. The integral of dx is delta x, evaluated from the initial position to the final position. So this is a delta x, xi, xf. And let's plug the bounds in. Vf squared over 2 minus vi squared over 2 is equal to a times xf minus xi. Let's multiply both sides by 2. Vf squared minus vi squared equals 2a xf minus xi. This is our third kinematic equation, derived from the definition of velocity and acceleration. I will place that in the box. Vf squared equals vi squared plus 2a delta x. And this is the third one. There is one left, and not much calculus is involved with getting that one. We just have to remember that the formula for an average is let's see, equals 0 to n over n. In our problem, that's the formula for the average of any list of things x sub I. So in our case, we have an initial velocity and a final velocity, or another velocity at some point in time. Doesn't really matter. But the point is that there are two things, right? So we add them together and divide by 2, and this is equal to the average velocity over the trip. It's also a fact that from the definition of velocity, the average velocity is delta x over delta t. If t0 is 0, then this is delta x over t. Multiply the average velocity times time, and we get the displacement. The average times time equals delta x, and v average is what we have shown right here. Vi plus vf times t over 2 is equal to delta x. Not much, actually no calculus involved here. This is our fourth kinematic equation. I shall put it in the box. Vi plus vf t over 2 equals delta x. So same results as last video, except this time we used calculus to get the majority, 3 of the 4 kinematic equations. In the next few videos, we will be taking a look at how we can use these to solve some very basic physics problems. Pretty much any kinematics problems can be used, or can be solved using these 4 equations. We're going to start off with some one-dimensional kinematics problems, and then we'll move on to two-dimensional projectile motion problems using these exact same equations. Thank you for watching.